Today we're going to slay compression, represented by the brick, and we're going to come out with something new. Something to do with tension, C6XTY.
This is definitely within the realm of possibility. My name is Sam Lanahan, and I'm the inventor and president of FlexTegrity. C6XTY is really a continuation of a developmental process that began over a decade ago. And it's the latest manifestation of an assembled fabric that results in strong materials and lightweight structures. The geometry of the C6XTY, we find it in nature. It occurs naturally. Where we find it is in some viruses, perhaps we're more familiar with it as called a fullerene, a bucky fullerene, or a buckyball. But we recognize that shape as a soccer ball. So to us, it's a soccer ball. We just need to scale it up 100 million times. But the properties of the structure are what really make it work. And so it's not the C6XTY by itself, it's that it does two things. It's a stable geometry. So when we look at the houses and the buildings that we erect today, they're all based on a cube or a rectangle, which has no inherent structural stability. These things will blow down, as we know, but the roundness, the sphericity of the C6XTY is what gives it the stability. And actually it's the distribution of the pattern on the surfaces, which is the pentagons and the hexagons that we recognize in the soccer ball, that is the core, the heart of this, and why this is a geometrically stable shape. And the soccer ball is made up of 20 hexagons, and it's made up of 12 pentagons. So what I've been able to do then is to say to myself, well, how many hexagons do I need? So I've taken 8 of those hexagons to use as a locking system, and then I use the other 12 hexagons to use as the tensile connectors to the rest of the lattice elements. The second property that we get from this shape is its symmetry. The five-fold symmetry as described by this particular molecule results from placing an axis. So you think of just an axis in here and an axis down here, and we can rotate this into 5 unique locations as we spin through 360 degrees, and they are mirror images of one another. And what it allows me to do is to bound the icosahedron, in this case the soccer ball, inside of a virtual box. We can think of this as being bounded by a box-like structure that surrounds this. So we get these tensile elements binding on either side of this, and that is what forms the lattice. So these become islands of compression. And what allows for the elasticity and the resilience of the structure are the tensile elements. And so we can design these tensile elements to have any properties that we want. They can be more elastic, they can be more spring-like, or they can be less elastic and more sort of rod-like, if you will, and steel. So this thing can be flexible or it can be very strong. I can't talk about structure without talking about tension and compression. And we can look at our universe and we see islands of compression everywhere. They're planets, right? And these are gravitational islands, if you will, but they're compressing together. And then the universe is also distributed in tension, things are pulling apart. These are coexisting everywhere and at every moment in our lives, tension and compression. We don't realize it. But tension and compression are also ubiquitously attempting to achieve equilibrium. They want to be stable. Heat to cold wants to stabilize. Things that are pulling apart want to be brought together. So it turns out that we can isolate compression and we can isolate tension, and that's what we've done. We've taken the ball, the C6XTY module, and we've isolated compression in a mathematically most efficient manner. So the forces of compression are actually being distributed around the entire surface of that structure. So it's acting in compression, and then we array that in a sea of tension, and that's what these tension members are. And so we've isolated compression into a sea of tension. This is very different from how we build today, where we put vertical uprights 2x4s operating in compression, right? And there's only so much length we're going to get out of that. We put a weight on that, and eventually it's going to buckle. So we're not going to build in compression, straight compression columns any longer. We're going to start building in tension. And tension is going to give us all kinds of advantages. One is we can start building prescriptively, right? I can make things flexible. Flexibility is what gives us resilience, right? Trees are resilient because they can withstand the wind. They sway and they bend in the breeze. That's what makes them resilient. The single most challenging question that I have faced from the very beginning is, what's the application? And let me give you a range of applications just to stimulate your imagination. I'm in a small village in a desert region, and there's a ravine. It may be only 10 feet deep, but it's sufficiently difficult to navigate that I can't get my pickup over it and up the other side, right, to get to the market. So I can't carry my watermelons to market. I don't need an engineered bridge that a civil engineer would design for an 80,000-pound semi to drive over, right? I just need something to get my watermelons to market. We now have drones with the photogrammetry already built in, where you can fly over an area and literally within centimeter level accuracy know exactly your points of contact. You could fly over this thing and get your elevations as well. That data could be transmitted back to local factories. You have basically 3D printers of sufficient size and magnitude where you just gang print these things. Because they're hollow, they're essentially hollow. They're essentially very lightweight, but very strong. You're using the right kinds of plastics. Then you pick this up by a helicopter, fly it, and drop it in place. Now, that village individual can get his goods to the market. And it's relatively low cost and relatively efficient to do. And so when we're starting to talk about the smaller scales, then we can begin to think about biological substances, or we can begin to think about things that might drape, fabrics that might drape. So where would that be useful? Well, if these were made out of ceramic, for example, they might provide a full armored covering of the entire body that was also flexible, that allowed someone to run, and yet it was very lightweight. But primarily, this is a ballistic vest that you can run in, and it has all kinds of other environmental controls. This is definitely within the realm of possibility, but this is certainly a fabric, an assembled material that can be assembled at all scales. And that makes it sort of universally, if you will, adaptable, because it's the same geometry at every scale, at every resolution. It just depends on the application and how it wants to be used. Sidewalks, for example, where we want to build in resiliency. So right now what we do is we just pour concrete. Well, concrete's anathema to the body. We're taking the skeletal structure and pounding it on rock. But if we build in a resilient structure into that concrete such that it gives way, it's a much more comfortable walking environment. We need to really rethink these, how the built environment is constructed, and whether or not we've adapted the right technologies for the human condition. The important takeaway from C6XTY is you can build virtually everything. Everything you can imagine can be scaled such that I can build it as an assembled fabric from the C6XTY and the tension modules. It's just a question of resolution. So we could make these things very, very small, and they would appear to you as normal materials, yet they may be lighter, stronger, less expensive to produce, so less expensive for the consumer, and they may be adaptive to all kinds of unique solutions that we haven't even contemplated. So one of the great advantages to these materials, of course, is that they're easy to produce, they're lighter, they're cheaper, and they're stronger. And so when we talk about making a material lighter, we're actually talking about reducing its carbon footprint, but we're also talking about reducing the very substance from which it's made. So that means that we mine less, we have to use less chemistries, we're introducing fewer toxins into the environment as a result of byproducts of manufacturing processes, etc. So this material reduces the carbon footprint by simply doing more with less. So Is C60 the wave of the future? Most certainly. We have to go this way.